attention to details that's gone into the design of this. We'd have the two ports, port 1 and port 2, and we do have them directly connected to the front-end couplers over here, meaning that these are fairly easy to replace if anything gets damaged. We have a very thick front metal plate here as well, adding rigidity to the entire structure, which is great. Now right away, if you notice, we do have our couplers outside of the main PCB of the network analyzer, and that's something that's different from some of the low-cost network analyzers we see. And there are several advantages to that. First of all, looking at the size of this thing and the fact that this starts from 300 kilohertz at the low frequency, this is almost certainly a resistive-based with some bridge-based coupler with a coaxial single entity differential conversion in the middle. Once we open it up, hopefully we will see and verify that. Now what this does is that it allows you to get much better isolation from the PCB itself. One of the problems with making a single PCB network analyzer is just a simple isolation between the two ports, and therefore a lowest level of coupling you can ever measure. In this situation, bringing this all out of that board and having their own mechanical chassis and aluminum body around them separates them. So if you look, each of these has 1, 2, 3 port here. So we have the incident wave, the reference, and the reflected, all coming from different ports going to the main board. So the main board at the bottom is basically completely mirrored on the top and the bottom, keeping these two as far away from each other as possible, which is a reflected wave, allowing them to have excellent isolation. So this is a really good idea and adds cost to the unit, of course, and adds complexity. But look at all these custom-made aluminum pieces, individually bent coaxial rigid cables. I mean, these are the kind of stuff you see at very high-end network analyzers. So I'm glad to see that. The main board at the bottom, I can open this at some point if there is interest to take a look at it. It's just simply going to have the two identical halves with the synthesizer, switches, and power control. So not very complicated, and the digitization on the IF side. There's a lot of custom paint parts, as you can see, but look at the way they've managed even the cabling of the fans and shrink tubing each one, every single thing. It's just really nicely done. The main board at the bottom over here looks like some FPGA or something at the bottom that just interfaces to the USB port and everything else, and everything else is going to be underneath this cage over here. Interestingly enough, there is a reference in port here, which is not populated. I wonder if you could just drill a hole in here, add your own reference, if all the parts are there for it to lock to an external reference or not. I'm not sure why this is not used on the outside, but everything else looks really nice. The thermal solution is a little bit unusual. We do have these 3 fans that blow this way, but there are no fins anywhere. And I suspect that that's probably enough to just bring cold air over here, push it out from the back of the unit. Seems to be working just fine. We do have custom little PCBs in the front for the power button, as well as the lights indicating the ports, but overall really nicely put together. Let me know if you want to see inside of this. We can take it apart further, but let's take a look at this to make sure that the coupler is what we think it should be. And here's our coupler, and exactly as expected, this is a resistive-based coupler with a single entity differential conversion using a coaxial cable surrounded by ferrite beads. I actually showed this in a demonstration in one of the previous videos of how surrounding that coax with the ferrite bead extends the low frequency single entity differential conversion capability. And once that's differential, you can do the coupler at the output here. So you have two resistive couplers at the input and the output, and the wave enters in this side. There are some RF absorbers on the sides too, or they could be further ferrite beads. It's hard to tell, but this cavity here is really designed to extend that low frequency as low as possible and have a good isolation. Another small advantage of having this outside is that if there is an overload condition and you burn up these resistors, which can happen, you could just replace this or repair this tiny little PCB at the output without having to do anything to the main PCB of the network analyzer. So generally having these devices separately does give you that